just hear kind of, I don't know whether it's question of Zoom or something, but I don't hear it clearly what you, yeah, I'm ready, okay.
Well, thanks everyone for coming. This is the third lecture of Gordana, and thank you for giving us this lecture.
Okay, well, thank you for the, well, first of all, thank you organizers for inviting me, and okay, so you also don't clear very clearly. Okay, so yeah, thank you for inviting me and giving me a chance to talk about all of this. I just wanted to point out that actually a large part of what I was talking will be part of a book. So we are actually writing a book, which will be published by the Cambridge University Press. So this is the book which will be with Igusa or and Weyman. So large parts of what I'm talking about will be in the book, and of course there are some other things in there. Okay, so this is the part, and today, actually for this lecture, I found a few more things which I wanted to mention while I was going through that. So anyway, so today I said I was going to talk about prop pictures. So this will be kind of a lot of review. Q is a quiver. I will be talking about prop pictures of quivers Atilde. I don't put N here because of the number of vertices, it's always confusing with this N here. Okay, so anyway, it will be Atilde. We consider subsets Si. Subsets Si are subsets of the indecomposable representations with endomorphism ring K, but non-homogeneous. So it's non-homogeneous bricks. Notice it will include also modules in the tube which have dimension vector null vector, but not above it. So it's kind of, this is precisely, on the example, it will be clear exactly which ones I'm taking. So these SIs will be finite. We'll be adding one at a time, even though later I'll be adding kind of in clumps. They're closed under indecomposable subquotient. So they're closed under submodules and they're closed under a quotient, indecomposable. And there's no condition. So this is different from the talk that I gave on maximal green sequences. There's no condition on X now. Okay, so it is only that they're closed under indecomposable subquotients. And here's a nice choice of origins. It's not necessary to do this way, but this is the way we do. You can take simples in any order. Then after that, you take all modules of length 2 in any order. Among those, okay, so I'm only talking here. So we don't want to take homogeneous modules, right? Length 2, length 3. So everything has to satisfy these conditions. And then the picture, well, picture of each one just as it was defined many times. So I'm sorry I keep repeating over and over. You look at the beta i's for each of the betas here. You take union of these walls and you intersect with Sn minus 1. N was the number of vertices. So I should have written here that number of vertices is always N. I always use N to be number of vertices. And then with this LSI, they're all inside the larger and larger and larger. But then there's also the reduction process, which is this reduction process is kind of just a simple-minded reduction process. You delete what you are supposed to delete, but it is used in the process of proving and so on. And then we have this inverse system of pictures. And here is just exactly what happens. You start with simple. This is simple 1, 2 simples, 3 simples. And then here I added the P2. Then after P2, I added I2. After I2, here we add also module 3, 1. Okay. I'm talking about the A3 3 A tilde. So 3, 1 is already a module which is in the tube. Actually, S2 is also in the tube. So I want to discuss this a bit more. So notice the red one is the one which is in the tube. So this is DS2, and this is D31. And now when you look at these two, you can see here that this is 3.1, this is S2, and there's extension of these two, and the extension is a module of this form. So this is supposed to illustrate the shape of the module, right? So you can see that the circle is 1. Now, on the other side, you have 3.1 in top and S2 on the bottom, so you get this module. So you can see that when you look at these two modules, so once we got into the tube, we are still looking at regular modules, but now when we look at the extensions, we get two different modules as extension. On one side, we get one module, on the other side, we get the, notice is the curvature or orientation, to be more general, what tells us what are the extensions. So here you can see, and here's exactly the extensions that I wrote. S2 extends 3.1 and you get a module like that. And here's 3.1 extends 2 and you get a module like that. And these two modules both have dimension vector, null vector. Okay, so this is what happens once you get into this. So the point is that we are getting now more, okay, we don't have any more just pentagons, right? So we'll have now other relations like this, okay? And then of course, once you have this, then you can look, here is 2.1, here is 3.1, and there is extension of 2.1 by 3.1, and you get this module, which is actually our P3, which you could get also by taking 1 and extending this, and you get this module. Once you have that, well, you can look at this part here, and that is extension of 2.1 by 2.3.1, which is the same as extension of 3.2.1 by S2. So you add this one. Now the natural thing is you continue, you add this one because there is a nice extension here, and then you add this one, and then you add this one. And there's the beautiful picture that Tomoki, again, I have to mention Tomoki Nakanishi has a beautiful picture of exactly this part with all this, you know, technically nicely drawn, all these extensions one after the other. And then here's my somewhat more primitive picture, because this is how we started this work. Okay, so that is before, you know, I had iPad and computer and all this, and here's exactly, here's our 3.1, and here's, okay, so here's the domain of S2, here's the domain of 3.1, here's this module, which is extension on one way, extension of the other way, and here I drew many more modules in here, and you can also draw many more modules on this side. So this is just the same picture, but kind of, this is actually the picture they started the work with Moses, which I will be talking towards the end about this, because when we talk about infinitesimal picture, then we'll kind of concentrate on this part here. Okay, so now let me go back to the pictures and picture groups. So here we have inverse system of pictures, right? By adding more and more modules, and we get more and more d beta i's, which are the domains, or more and more c vectors if you want. And we get pictures and we get picture groups. And each of these gi, okay, has generators. Now generators are of course the modules which are in Si, okay? And yi's are products of the x's, which, and yeah, I already talked about it, and I'll just show on the example, and this is inverse possible, you know, epsilons are plus or minus 1, and it is essentially these relations. Either you go this x, this, and then inverses, or you say this is equal to that. And then, of course, there's the other one, which we saw many times and which I was really using here, that this module actually is extension of these two. And in simply laced, finite simply laced, these are the only two possibilities. But again, I'm emphasizing it is finite simply laced, because now when we got outside of finite, here we are in infinite type, we also have things like that. So, and actually this, what I pointed out on the example, the module on one side and module on the other side are different. So since we are now allowing both x, and the two sides correspond to different modules of dimension vector n, okay? So this is, so at each stage, so these are now finite groups. I mean, groups, finitely, not finite groups. I mean, finite number of generators, and we have relations which are of this type, or this type, okay? On this finite stage, we still don't have infinitely many things in between. And now, and then we have this group epimorphism. So we have inverse system of the groups. And then we take the limit of these groups. And this is our pro group. I mean, pro picture is the system of pictures, and this is pro group. I should have, okay. So this is pro group. Okay, so now I want to make some statements at this point about this group. And I will be talking about this group also later in relation to Lamp-Piliavsky's maps. And so I will be coming back to this group. But at this point, what I want to point out is that this group, oh, let me do this. Okay, this group, okay, so generators are all non-homogeneous bricks. Just to repeat, these are the pre-projective, these are the pre-injectives, nothing from the homogeneous tubes. And in non-homogeneous tubes, you just take things from the bottom up to the one which is still, which has dimension of null root, okay, but we are getting different modules that, you know, there's different module here and here and here. So you get these modules as I did in the example, okay? So these are exactly these non-homogeneous bricks, pre-projective, pre-injectives, and bricks in large tubes. So it's only up to this point. And so y, and at this point, our y, which is the set of relations, will be, of course, the old ones that we already had. We have this, and now we have things of this form, where you have infinitely many. And let me just go back. I'm going back to the picture just to point out where is it that it happened. So it is at this point, here we have P2, so domain D of P2 and D of S3. So on this side, so notice the way they're curved, which is the orientation, it tells us that this is the same as this. So I just wrote here, it's x of 2, 1 times x of 3, which is this, x of 2, 1, x of 2, 1, and x of 3. Notice this is the orientation, x of 2, 1, and x of 3 is the same as going from this direction, x of 3, and then you have to go through the infinitely many of these, which can be all described nicely. You come to 3, 2, 1, and then again you have to go through infinitely many of these, and then you get to x2. So this is this relation, which has infinitely many things here. And similarly, at this part, you have the similar, this is the 3, 2, and this is S1. So you can do S1, 3, 2, or 3, 2, and infinitely many until you get to S1. So these are these infinite relations. And I guess this is what happens in topological groups. So it's not our standard finitely presented groups, but in topological groups, you do allow these infinite sequences in relations. So this is what I wanted to say about this group. Now, I will be coming back to, as I said, I will come back to this. I will come back also to representations of this group. So representations of this group. So I'm talking now about this group. Okay. So we'll be talking about representations of this group in relation to Lem-Piliavsky's maps also, and about semi-invariant, about this part. Okay. Okay, but before that, there are a couple of things that I want to point out which are being used. So first, I'll mention this for finite type. Okay. So in finite type, well, here's example of finite type. So we know that each of the triangles or the highest simplices in the picture group, in the picture correspond to clusters or cluster tilting objects. So here, and I want to talk about labeling of these clusters by group elements, which I already used when I talked about maximal green sequences, but I just want to recall this because I will need it again, okay? So again, here's our LQ as before. Walls are D betas, where betas are positive roots. X betas are element generators of G, and G is given like that, and the relations are only that. I'm talking about finite type here. Okay. Now the point, okay, so here's the part that I want to say. We want to label each cluster or cluster tilting object. So that means each triangle here by an element of the group, which we call GT. And the natural thing is to take, it's a product of walls that one has to cross in order to come to that. So here's the example. So we take the outside, I'm taking the outside cluster, which is initial cluster or initial cluster tilting object, which is shifted projectives. We take this to be identity. And then to come to any of the clusters, you go through the walls. So here's the picture. So here's the G, so element of G corresponding to this cluster. So the cluster is P1, P2, and P3 shift. So G of P1, P2, P3 shift. I can take it to be product of X corresponding to S1, X, S2, and or I can take it as product of these, and that is precisely the relations which allow us to do that, okay? So here is the statement, right? So each of GT is labeled by the product of X betas, where betas are the walls that are crossed or C vectors that are crossed. And so we also have that the G of the cluster times the X at beta K. If we do green mutation at beta K, then then we have to take a G of the cluster and multiply by X of beta K, and we get the G of the mutated, which is just, if I take G of this, I multiply by this and get the G of that. It's just the way it is defined here. So, but the point, okay, again, the point of this is, which I will use later, so that's why I want to kind of emphasize. So the point is that label each cluster or cluster tilting object by an element of the group. So you notice these are elements of groups which label each one of these clusters, okay? So even though we do have all other, and then this is the rule which is used essentially to prove various homomorphism properties. And here's the homomorphism property. Okay, so while I was going through this, I just realized that we do have this proof, which is something that I kind of mentioned, but did not state clearly. So anyway, in this, our book, which is not which we are finishing or preparing, okay? So we proved that there is this homomorphism, and I will kind of expand more on this kind of homomorphism. Okay, so there's a homomorphism. Here I'm talking about the finite type, but the similar homomorphism will be used also for A tilde. So here I'm talking about AN, but I will be talking also about A tilde. Okay, so notation, this is a standard combinatorial notation that people like to use. So you have your quiver, the vertices 1 through n, and then the epsilons are plus or minus 1 depending on, so we take epsilon is plus 1 if the arrow goes from I plus 1 to I, and epsilon is minus 1 if the arrow goes this. So this is plus and this is minus. Okay. And beta I, again, this is the standard, I guess, combinatorial notation for the beta i's, because these are all modules. It starts with EI plus 1 and it goes into, I mean, beta ij starts with EI plus 1 up to EJ. And then we define, so here's the homomorphism that I'm defining. And again, it's quite natural. So we define homomorphism from the picture group to the unipotent group, meaning group of n plus 1 by n plus 1 with ones here and integers here and zeros here. And we define it to be the group xij at epsilon I, meaning an ith place and jth place, you put epsilon I. This is one homomorphism. There are some other homomorphisms which also work quite nice, but this is this was the easiest one to describe, okay? So that means each of my beta ij's is, x beta ij is sent to a matrix like this. And then one checks that this is a group homomorphism. One proves that this is a group homomorphism. Now, why was this important? Well, for many reasons, but one of the things that was in, so this is something which I mentioned for straight orientation, and then I did not, for the non-straight orientation, I actually wasn't quite sure, and now I found that we already, wrote, so this is true. Okay, now why is it true? Okay, well, I was talking about homology and cohomology of the picture group. So here's the picture group for AN. And then we have cohomology. And then I was discussing about massey products. And actually, when I talked first time about that, there was kind of discussion, are they all the same or not? Are they all zero or not? Okay. So now finally with this theorem, and after talking to Kent Orr and Igusa, okay, we have that massey product in the cohomology of the picture group here is zero, or Kent Orr prefers to say contains zero because it's not really uniquely determined. And now the proof for that is the consequence, actually, which I didn't know earlier, but Kent pointed out. This is a consequence of Dwyer's theorem, where Dwyer's theorem says that, okay, I wrote originally, if there exists this homomorphism, then massey product is zero. But actually, this is if and only statement. So it's a really strong statement that massey products are really determined by whether there is a homomorphism of the group into UN plus 1. So this is so the exist phi is necessary and sufficient condition for massey product to be zero. So I just wanted to add this because that was something which I kind of mentioned earlier, but I really didn't have the precise statement. So this is actually now the precise statement. Okay. So this is, so that was digression to a finite, to a group AN, which is of course, finite type. And now I want to go back to A tildes, which are of infinite type. And I want to talk about representations of those groups. So in order to get to Atilde, right, and group associated to Atilde, we have all these groups in the steps in between, which I call GK. So GK is a picture group of LSK, which was this, okay? I'm just going to modify slightly SK, okay? And then I want to talk about representations of these groups, and it will be kind of similar to what happens here in finite type. The only thing is now it will have systems of these groups, okay? So to talk about this, okay, let me see. So we consider the following picture groups. So instead of adding one element at a time, I'm just taking SK to be set of all X, of course, non-homogeneous bricks of length which are less than or equal to K. So I'm taking S1 to be the simples, S2 to be all the modules of length 2, and so on. So the iteration process is faster. So then the picture space, of course, will be this LK, which is union of all the domains of X's in dim X, and intersection with Sn minus 1, and GK is the picture group for that LK. Okay. Now I want to talk about representations, but it will not be Z representations. Now we want to look at the ring RK, which is ZT mod T to K plus 1. And we want to define n-dimensional RK representations of those groups. And now it will be again quite kind of just generalization of the previous one. So PK will be a homomorphism from GK to GLN, and we mod out by T to K plus 1. Notice it's the same K. So when we are at the G1, we just mod out by T squared, at G2 by T cube, and so on. So we have these different rings here, okay? Now, the notation is just extended notation of AN. So this was our AN, and because it's AN tilde, you just extend and you have the periodic part here. Okay. And now we define, so again, the definition is just as it was. Okay, so first, let's say for just simple, X of SI, it will be just I plus 1, and we put epsilon I, but now we put T here. Okay. And actually, here's the general formula, which says that X of beta ij, so again, beta ij, it starts with I plus 1, and it goes all the way to j, it can go. So X of beta ij will be a matrix, again, in the entry I, in the entry j, epsilon I, just as it was in the finite type. The only thing is that you here multiply by T to j minus I. So that means the matrices will now have plus minus and also powers of the T's. Okay. And that will give a representation. So this will give a representation of the group GK, which we obtained at the kth stage, right? So we started, here's at G1 is corresponding to this, G2 is corresponding to that. So you do step by step, and you get representations of each of these GKs in, and they're always n-dimensional representations. So notice they are n-dimensional representations, but in these rings RKs like that. Okay. So what we have now, we have this system of groups, we have system of representations or morphisms. Now, our group that we are concerned about is the G, which is the inverse limit of all of these. And of course, here we have we have these rings. And then of course we have Z with double bracket here, right? So here we have finite T to K plus 1, and here we have power series, and we have GLNs here, and we have maps between the corresponding GLNs, and then we have this GLN over the power series, and we get a homomorphism from our group, our pro group, which is obtained from all of these groups. So from this group to GLN over Z with power series. Okay. Now in this, actually there was a part that we referred also to Lamp-Piliavsky, and now I want to mention again Lamp-Piliavsky. Okay, so Lamp-Piliavsky also look at the GLN over Z double bracket T. And they also have a homomorphism to that group. But what they have, the group that they're starting with here is the group of infinite. So now they're infinite and periodic unipotent matrices, Z matrices. So they have these infinite and periodic unipotent Z matrices. And then they have a homomorphism of that group to GLN ZT. Now we have a homomorphism from our picture group of this inverse limit. I refer to this as picture group, but I mean a pro-picture group, actually this inverse limit of our groups to GLN Z. So we have this and they have this. Okay, where these two are the same. So the question is, what is the relation between these two? Okay. So first of all, when we look at the picture group, now I want to go back to the comment that I made, that if we look at cluster tilting objects, so each cluster tilting object, which in our pictures was a triangle, or we can say the highest level, highest dimensional simplex, corresponds to an element of a group, right? So this is what I pointed, I kind of drew carefully on a finite type or AN, but this is true at each stage. When we have the cluster tilting objects, we get these elements of the group which correspond to each of the cluster tilting objects. So notice, sometimes I talk about elements of the groups as being our walls or corresponding to the walls or corresponding to C vectors, but then the products of those also correspond. So the particularly nice products, especially if you go through green sequences, through a sequence of green mutations, they correspond to cluster tilting objects. Okay. So this is the first thing that I want to point out, which I pointed out on a finite type, but this is what is used here. Now, the other part is that, which I'm not talking about here, that cluster tilting objects over A tilde, maybe I should add here, cluster tilting objects over A tilde correspond to n periodic trees. Okay, so this is the part that I am not, okay, let me, so cluster tilting objects. So you see, elements of the group correspond to cluster tilting objects. Now, cluster tilting objects correspond to n periodic trees. This is the part that I'm not describing at all. It's described in various papers. So what is known, and there were several papers by other people which talk about, if you're in AN, it was well known that in AN, you can look at binary or co-binary trees. And so binary or co-binary trees, and they correspond to cluster tilting objects. So in finite type, in AN, this is well known that co-binary trees correspond to cluster tilting objects. Now, what we have here, because we are not in finite type, that you have to look at n periodic trees, and they correspond also to cluster tilting objects here. So there is a correspondence here between n periodic trees and cluster tilting objects. I find the description to be technically too complicated, and actually I tend to forget the precise definitions because it is very combinatorial. But there is this correspondence. And then there is this is the star here, which talks about this correspondence, which is described precisely. And then there's the other part, which to each n periodic tree associates a LP matrix, LP meaning Lamp-Pilievsky matrix. So again, for trees, there is correspondence to matrices, to finite matrices, for trees of AN, corresponding to AN, to admissible trees. N periodic, I forgot to write here, N periodic, it should be, admissible trees. Okay, so it is only about admissible trees. Okay, so n periodic. So this is just a more general version. So the part that is kind of easier to write is that for admissible trees, there are associated matrices. And then for n periodic trees, there are associated periodic matrices. And this is actually the process. So certain elements of the groups which correspond to cluster tilting objects correspond to these n periodic trees. N periodic trees correspond to LP matrices, and this is the correspondence that LP matrices, which is the Lamp-Pilievsky's map going here. When we follow this way, they correspond to the same matrices that we have here. So this is how this homomorphism and this homomorphism are related. Okay, so that was another thing about these pro pictures that I wanted to point out. That we so how they're I guess in short, I mean, I wanted to recall how they're constructed as the inverse limits of the pictures, where the pictures are inverse limits of the group, picture groups which are obtained as inverse limits of the pictures. And that this is kind of this part. And then I wanted to relate this to this Lamp-Pilievsky, which is known, the homomorphism that they have here. And that is how our group is related, or this homomorphism is related here using the representations. Okay, so so this looked a little bit, okay, so I talked about representations just quickly. I talked about the homomorphism of the picture group for AN to the unipotent group because I wanted to talk about Massey products being 0. But then also this homomorphism, group homomorphism, which appears here, can be extended in some way to the representations of each of these GK groups, which are not now corresponding to hereditary, well, they're generalizations, right? So to each of these GK groups, and we look at the representations of each of these GK groups over these rings, instead of just Z representations, now we look at over these rings, we get the appropriate homomorphisms, which induce a homomorphism here. And then I wanted to relate this homomorphism that we just got here to the homomorphism of Lamp-Pilievsky and in the process, there are all these parts which are kind of important about the cluster tilting objects and periodic trees and corresponding matrices. So that is about the prop pictures. And now I want to go back. Okay, I want to talk a little bit more about infinitesimal semi-invariant pictures. So as I said, these will be called null pictures. So as I said, this is the work that it was Moses Kim who started, who said, well, how about if we study, I mean, the term infinitesimal comes because he suggested to study tangent space to semi-invariant picture. So this was Moses' idea, and then we all joined. Okay, to study tangent space to semi-invariant pictures. So we are looking at hereditary algebras and at null vectors. So it will be tangent space at null vector. Okay. Now, again, here's the definition that we always talk about, d beta. This is the standard definition of the walls that we always look with Euler product being 0 and Euler product less than or equal to 0. But now on this d beta, we want to look at the particular v, any v, but actually our any v will be our null vector. So we want to look at the v at d beta and look locally what happens around v. So here's the definition: d0v at beta is set of all w's in Rn such that there exists epsilon such that this is in d beta. So it's a typical tangent definition. And then we take all of those, but notice now this is happening in, because these are, okay, this will be in tangent space, so it will be in n-1, and then we want to intersect with sphere n-2 in order to get pictures. So this is this picture. Notice it goes down 2 dimensions. So we are starting with with quiver with n vertices. We have everything in Rn, then our picture, original picture, semi-invariant pictures were in n-1, Sn-1, and now these infinitesimal pictures will be in Sn-2. So we go down by 2 dimensions. Now, another definition, which is actually equivalent to that, okay, the other definition, which is algebraically easier to deal with, is that you look at all w's in V perp. And at this point, we start using ordinary product. It is just question. This uses Euler product, so we are always using dimensions of vectors here. Here we are using dot product, so we're using G vectors. So it is just the switching from here to here is essentially switching from dimension vectors to G vectors. So dv perp, so this perp is really defined as the ordinary dot product, okay, is defined like that. And then corresponding picture is just intersection, union of all of these intersection with Sn-2. And then the theorem is that this tangent space, which was defined kind of epsilon way, is the same as this perpendicular picture, which is defined in algebraic way. And this is the way we like to look at. I mean, this was Moses' idea to start this way, but then we proved that this is this, okay. And the V, so this is, if we have the domain d beta and we look at the particular V, and we look at what's happening at that particular V, at the tangent space at that particular V, okay? So now our particular V that we are interested in is a null vector. So we'll be looking at G, so we take null vector. Because we are talking about the dot product, we will be using G vectors. So this is a G, so N is the null vector. We take the G vector of the null vector, and we take the null picture, which is what was defined here. Okay. And we study now this null picture. So let me just go quickly to the 2 examples. So, as I said, this is the null picture. So this was the example that we started our Atilde with 3 vertices, right? N was 3, N is the number of vertices, which is 3. So we had the semi-invariant picture was on S2, as I drew before. Now, tangent space will be also in R2, so the tangent space will also be 2-dimensional. But the null picture is going is taking the tangent space and intersecting with 1 step smaller s. So the null picture for our A tilde with 3 vertices will be in S1, and it will look like that. So this is what we see here is the tangent space, but then the green dots are the dots which are now on S1. So these green dots correspond now to null picture. And let me just, yeah, this is what I'm talking about. And now, when more interesting version we see, okay, so more interesting is when we take n is equal 4. Somehow, n 3 vertices is a bit too small, right? Because we're getting everything on S1, and I usually don't like when we get things on S1. I like when things happen on S2 or higher. Okay, so we are starting with n is equal to 4. Our semi-invariant picture will now be on S3, so on sphere S3, which means that the tangent space will be isomorphic to R3. So the tangent space is 3-dimensional. And now null picture has to take the tangent space and intersect with a sphere in here. So null picture will be on S2. Okay, so for this quiver, the null picture will be on S2. And so this is what it will look like, and I'll describe in more details, but I just want to point out that instead of having here just the points like this, we are going to have our nice circles, which will be these, the d betas intersecting S2 and so on. And also what I pointed out here, I just put different colors, okay? They will correspond, these parts here will correspond to the null vector, but they will correspond to the different modules which have the dimension equal to null vector. So this is what I'm emphasizing is that we are looking at the modules which have endomorphism ring K, but they're not necessarily rigid. So this is what I was saying about our choice of modules. Let me just go back. I thought I had a nice, yeah, okay. The modules that we are considering are here, here, and here. So now we are only looking at the module. So this semi-invariant pictures will deal with what's happening right here, okay? And we'll be using strongly the modules which appear in these larger tubes. And now let me just go back to that. 49, okay, I'm almost finished. Okay, so here's this example, and then I'll state the theorem. Okay, so here's the example. So notice, and I want to point out, so that for this quiver, we have 2 tubes of rank 2. Okay, so of course, null vector is 1, 1, 1. And the G of null vector is 1 minus 1. And then the perpendicular space is 3-dimensional. And then we are drawing this on S2. And this is just projection of S2. Okay, so here is one of the tubes which has 2, 1, 4, 3. And then, of course, 2, 1, 4, 3. So, and then the other tube has 4, 1, 2, 3, 4, 1, 2, 3. Okay. And then we also have the null vector. So now the picture, the infinitesimal semi-invariant picture, okay, will be this. Okay, so this is our now our chambers of regular wall, the chambers of regular walls. Okay, so first, what is interesting here is that this is not simplicial. Okay, so this is something which happens in a different way now when we look at this semi-invariant this kind of part which is just related to the null vector. So this is not simplicial, okay? And so if lambda is stem hereditary, so the chambers of regular wall and chamber structure, which is example here for this, are in bijection with support regular clusters. So we will have here support regular clusters, which is kind of generalization of the tau cluster tilting. So these support regular clusters will consist of M, P plus, and P minus. Okay, M will be just a regular support tau tilting module, but now only in the tube. So that means my M will be either this or that, or this or that, right? It could be this and this, but just tau regular in the tube. I mean, these are small tubes. If I took larger, if we do on larger E something, then we'll get larger tubes, right? But or larger A tilde, we could get larger tubes. Now P pluses and P minuses, this P plus kind of corresponds to, in the tau tilting, you know how in tau tilting you have a module and you have the projective part such that projective doesn't map to the module, or you can take about projectives which don't map to tau M. So this is actually the division between P's which don't map to tau M. So M is just the ordinary tau tilting part which is happening in the tube, okay? And then these P's are interesting because they are actually not projective because we are in the tubes, but these P's that are here correspond to projectives in corresponding Nakayama algebras, which I didn't state here. So here we have one tube and here we have another tube. There is a formal notion, and this tube corresponds to a Nakayama algebra of rank 2, and this corresponds to another Nakayama algebra. This picture corresponds to co-amalgamation of the pictures for these two Nakayama. So we have Nakayama algebra, picture for this, the formal co-amalgamation process, which gives us this. I talked about that before, but for this talk, I guess I didn't prepare, which is essentially, you see, one Nakayama will correspond to this part, the other Nakayama will correspond to this part, and then co-amalgamation is the formal way of putting them all together like this. Now these P's here, which we call projective, they'll correspond to choosing projectives, choosing a projective in this Nakayama and a projective in this Nakayama. So it can be it will be pairs of projectives. So now back to support regular clusters. Okay, so support regular cluster will have something which is tau regular, and then it will have these interesting projectives which correspond, we call them projectives, they're not projectives, but they're pairs of projectives in associated Nakayama algebras. And one of the P pluses corresponds to P plus corresponds that P does not map to tau M, so it still belongs to the tau tilting part. And the other P corresponds to P which don't map to dim M, which is like in the tau tilting story when you take shift of a projective, okay, or take m comma p and take p. So here's just each vector in p plus and p minus correspond to collections of regular, projective, regular quasi-simples in these tubes, and regular quasi-simples in these tubes correspond to the projectives in the corresponding Nakayama algebras. I guess I didn't write this part, but actually I wrote at some point, but okay. So this is okay. So this is the story. Okay, so now just to kind of summarize. Okay, so today I talked a little bit about finite type. Talked about pictures, picture groups, right? Which the whole book is going to be about these pictures and picture groups. So a large part, most of these parts are going to be part of the book. Okay, this part on infinitesimal semi-invariant pictures is really to deal locally what's happening around the null vector and what's happening with the regular modules at the null vector. And it is interesting because this is this joint work, right? And it is interesting because the wall and chamber structure becomes a different wall and chamber structure. It's not anymore simplicial. And furthermore, you also get these now support regular clusters. There's one support regular cluster, which, for example, here has 4 terms. So you get larger for clusters. Okay, so it is definitely different than what we had before. And I think at this point I do want to stop. And thank you for anybody who came to my talk and anybody who was patient to come to many of my talks.
So, are there any questions in the room? Are there any questions in this room?
Okay. Well, again, thank you all for coming to my talks, and thank you organizers for organizing, and thank you for inviting me. I just feel like I should thank again.
Thank you very much. Well, if there's no questions for Gordana, let's thank again.
When is the book ready?
There.
Oh, when is the book ready? Okay, well, I guess this, giving this series of talks really inspired me. And while I was preparing the talks, I was really revising many parts. So I hope, and we all got, and then talking also to Kent and, about messy products, Kent got excited. So Kent and Kiyoshi are adding parts about messy products. So I don't know when it will be ready, but it's definitely, giving these talks kind of will speed up the whole thing, because I think we all got excited about trying to finish it. I mean, it is about 150 pages for now. So, it will require editing, but it's definitely now seriously in progress.
Thank you very much, Gordana, for this, and see you soon.
Okay. Okay. I guess you are going to turn off the things, right?